Module 2, Arithmetical Algebraic Equations, Differences, and Summations. Take a moment to internalize the list of goals for this module that will lay out the foundations of differential equations, not because you don't know them, but because you will see them different than when you covered this topic at school. Let's start with arithmetic and algebraic equations. The four fundamental operations in arithmetic are addition, subtraction, multiplication, and division. These are some of those examples that you will find really trivial and not very exciting. There are myriads of mathematical curiosities, and the one presented here is only one of them. Knowing that the inverse operation of division is multiplication, we are going to take the approximation of 1 over 7 to be 0.142857. If we multiply this number by 1, 2, 3, 4, 5, 6, and 7, a pattern will emerge. Did you manage to see it? If you didn't, or even if you did, here is anyways. You can now pause the video and give yourself some time to go through the four questions listed here. We're going to do something more exciting as well for multiplication. Starting with 2, we are going to multiply it by itself, as shown here, 10 times by itself. So we are going to get to the final result of 1024. 1024 is equal to 2 to the power of 10, and it is used to designate 1 kilobyte in computers. This, as we'll see, is going to bring the very important concept of exponential growth. Subtraction can also be made more thrilling. And what better than money, of the lack of it, to illustrate this concept? Assume you open a bank account with $1,000 and with an authorized overdraft for the same amount. If there are no additional deposits ever again and the bank doesn't pay you any interest, if you start withdrawing consistently $100 per month, by the 11th month, the account will have a zero balance, and by the 21st month, you will have a $1,000 debt. The last of the fundamental operations brings us to the fascinating feature frequently found in nature, the golden ratio, which happens to be closely approximated by the Fibonacci sequence. In the Fibonacci sequence, each number is the sum of the previous two integers. If starting with 0 and 1, we can start producing the sequence of numbers that are found by adding the two previous ones as shown here. We stop the sequence at 21 as those numbers are going to be used to build what is known as the Fibonacci spiral. Dividing the last two digits, 21 and 13, gives 1.615 approximately, which is very close to the golden ratio that is approximately as well 1.618. As for the sequence, it is built by using those numbers. No details are going to be given here on how to do it. The idea is to illustrate the concept. And now you may ask yourself, so What is the fascination here? Well, wouldn't this remind you of the Nautilus shell? The golden ratio can be found in other places in nature, such as flowers or pine cones. Painters, writers, and architects have also used it in the past. This is an invitation for the learner to look it up. In algebra, numbers are changed by letters, at least some of them. The usefulness of this lays in the ability to generalize concepts into formulas, some examples of which are displayed here. The addition is the summation of two or more numbers, and in exponentiation, the exponent y indicates the number of times x is multiplied by itself. But that is too easy, dry, and unappealing, so I will now demonstrate that 1 equals 2. Starting with x equals y, we multiply both sides by x, add x squared, then we add the terms on the left hand side of the equation, subtract 2 times x times y, add the terms on the right hand side, factor the common terms, and then we can cancel the terms that are identical to get to the final result, 2 equals 1. You may say WTF, which, as you know, stands for where is the flux? Unless you encounter this during your school years, it will be an interesting exercise to figure out what happened with the 1 equals 2 demonstration. Back in 1914, Sylvanus Thompson wrote a book titled Calculus Made Easy, being a very simplest introduction to those beautiful methods of reckoning which are generally called by the terrifying names of the differential calculus and the integral calculus. Derivatives and integrals, as presented in this course, follow the same principles that guided Thomson when he wrote his book over a century ago. I know the cover is not that exciting. Anyways, and as a way of introduction, here is a quote from the prologue. Some calculus tricks are quite easy. Some are enormously difficult. The fools who write these textbooks of advanced mathematics, and they are mostly clever fools, seldom take the trouble to show how easy the easy calculations are. On the contrary, they seem to desire to impress you with their tremendous cleverness by going about it in the most difficult way. Let's start with derivatives. Derivatives are a little bit off. dx is read as dx, or dy is read as dy, etc. Nothing beats audiovisual aids. Take a look to this animation that illustrates how a day as a whole is divided into hours to represent the same whole partitioned into 24 equal parts. It doesn't change the whole itself, it just changes the way we refer to it when it's shown in minutes. The sizes can be smaller and smaller until they become, in mathematical jargon, infinitesimal. Integral is the summation of the little bits of, and it is represented by an elongated s. Integration of all the little bits of amounts to add them all to recompose the whole. For all practical purposes, it's like running the animation backwards. This concludes the second module with the hope that from this point onward, you are not going to be afraid of integrals and derivatives anymore.